Picture a beach, not a metaphor. An actual beach, wet sand packed firm at the waterline, the rhythmic percussion of shallow waves pulling back across gravel, the smell of brine carried on a warm wind that is just thick enough, just warm enough, to be called an atmosphere. The year is 3.5 billion years ago. The star overhead is younger, angrier, and putting out roughly 30% less energy than it does today. And the beach is not on Earth, it is on Mars, a beach that no one was alive to walk. Evidence of a world we didn't know existed until a Chinese rover, on its very first interplanetary mission, drove across the buried remains of that shoreline and fired radar pulses into the ground and heard something extraordinary come back. The radar said beach, it said ocean, it said this place, which looks like nothing but frozen red dust, was once something else entirely. And here is what I want you to hold on to as we begin, because it will change everything that follows. That beach is 3 billion years old, not 4 billion, from Mars's earliest and wettest era when most scientists expected to find water. 3 billion, buried under 10 meters of accumulated planetary debris, perfectly preserved in the way that only a dead, cold, geologically quiet world can preserve things. Still angled at exactly 15 degrees, the same inclination as beach sediment deposits on Earth, as though the ocean retreated last week rather than before the first complex life on our own planet had even evolved. How long did that ocean last? How large was it? What mechanism sustained liquid water on a planet that was already losing its atmosphere, already losing its magnetic shield, already cooling from within? And the question beneath all those questions, the one that planetary science has been circling for half a century, without resolution, was anything alive in it? Mars lies to you. It does so with magnificent geological commitment. The surface you see in every photograph, that bone-dry, iron-oxidized expanse of regolith, the cracked plains baking under a sun that delivers just enough energy to make the temperature swing violently, between -70 and +20 degrees Celsius in the course of a single day, the twin polar caps of water ice and frozen carbon dioxide that shimmer in seasonal cycles but never melt into anything remotely poolable, all of it presents itself as something that has always been exactly this way: eternal, inert. A world that never worked and never really tried. The lie is so convincing that for most of human history, we accepted it without question. When Giovanni Schiaparelli mapped what he thought were canali on Mars in 1877, channels in Italian, a word that English-speaking journalists immediately and disastrously translated as canals, implying deliberate construction, the scientific establishment's reaction was either dismissal or romantic overcorrection into fantasies of an advanced civilization building planetary irrigation networks. The actual truth, which nobody at the time had the instruments to see, was simultaneously more mundane and more profound than either camp imagined. Mars may have had natural waterways, carved by genuine geological processes, more extensive than anything Schiaparelli's telescope could have resolved. But strip away the romance, and you are left with the numbers. And the numbers are immediately sobering. Mars today maintains an average surface atmospheric pressure of 0.6 kilopascals. That is less than 1% of Earth's atmospheric pressure at sea level. Water at that pressure cannot exist as a liquid on the Martian surface under any normal circumstances. The temperature-pressure combination places virtually the entire Martian surface below the triple point of water. The specific combination of temperature and pressure below which liquid water is thermodynamically impossible. If you poured a glass of water onto the Martian plains today at a mid-latitude location, it would not pool, it would not trickle. It would immediately either flash freeze or sublimate directly from liquid to vapour, depending on the local thermal conditions. There is no gentle intermediate state. The phase diagram does not permit it, and the atmosphere itself is mostly carbon dioxide, 95.3%, with 2.7% nitrogen and barely 1% oxygen. Breathing it would be equivalent to breathing vacuum for practical biological purposes. The ultraviolet flux reaching the surface, unfiltered by the trace atmosphere, is sterilizing at the molecular level. Organic compounds on the surface are destroyed by perchlorates and oxidizing radicals within years of exposure. The radiation environment at the surface would deliver a lethal dose to an unshielded human in approximately 200 days. This is the Mars we know. This is the Mars our rovers drive across. This is the Mars our orbiters photograph. This is the Mars that has been sending us data for 50+ years of spacecraft missions. It is, by every measurable criterion, a dead world, except for one thing. Look at the surface closely enough, really closely, with the kind of topographic resolution that only came available in the late 1990s when the Mars Global Surveyor's laser altimeter mapped the planet centimetre by centimetre, and the lie begins to crack. The northern hemisphere of Mars sits, on average, approximately 5 kilometres lower in elevation than the southern highland terrain, not 500 metres lower, not 1 kilometre. 5 full kilometres of crustal depression, creating an enormous low-lying bowl that covers roughly 40% of the planet's total surface area. The northern lowlands have a name, Vastitas Borealis, the northern waste, but waste entirely mischaracterises what that terrain represents. Geophysically, an enormous low-lying basin on a rocky world with a gravitational field is not a waste. It is a reservoir waiting to be filled. On a world with liquid water and an atmosphere capable of supporting it, that basin fills. Gravity does not negotiate with geology. It simply applies force over time, and time is something Mars has had in abundance. And alongside the topographic evidence, look at what the surface features say. Valley networks, some stretching 2,000 kilometres, that drain unmistakably from the southern highlands toward the northern lowlands. Deltaic fans, the characteristic splayed deposits of sediment that form where a river meets standing water and decelerates, dropping its load at the termination points of those valleys. Outflow channels so vast that geologists estimate the peak discharges that carved them were dozens of times the volumetric flow rate of the Amazon River. Minerals throughout the ancient terrain, smectite clays, sulfate salts, carbonate minerals, that require prolonged contact with liquid water to form. These features do not form in a desert. Not at that scale, not with that consistency, not with that mineral signature. So the first question this story must answer is, did Mars have an ocean? And the answer, as of 2025, is almost certainly yes. The beach Zhurong found is not a controversial interpretation. It is a geological fact buried 30 metres below the northern plains, angled at 15 degrees toward the proposed ancient shoreline, composed of coastal sediment with a structure that matches Earth beach deposits to a degree that leaves no serious interpretive alternative. But the first question is also the least interesting one. The more revealing questions are compounding behind it. How large was the ocean? How long did it survive? What geological machinery sustained it? What ended it? And what, if anything, lived in it during those hundreds of millions of years when the northern hemisphere of Mars was not a frozen desert, but a shallow, mineral-rich, energy-bathed coastal sea? Those questions will pull us through every chapter of this documentary, and not all of them will be fully answered, because not all of them have been answered yet by science. This is a field in active development. New data is arriving now in 2026 from missions that are still operating, and from analyses of data that has already been collected but not yet fully processed. We are not at the end of this story, we are at the first chapter of its resolution, and that to me is exactly where you want to be. Here is where the story becomes genuinely uncomfortable, in the way that the best scientific arguments always eventually do. The Mars ocean hypothesis, the formal, peer-reviewed, scientifically serious proposal that Mars once hosted a large and long-lived body of liquid water in its northern hemisphere, is not new. It has been argued, defended, attacked, revised, partially abandoned, and resurrected multiple times across 4 decades of planetary science. And the fact that it took 4 decades to build the kind of evidence that now exists is a story about the nature of scientific skepticism and the difference between being right and being provably right. The hypothesis was first proposed in serious scientific literature by NASA geologist John Brandenburg in 1987. Brandenburg called his proposed ancient Martian Ocean the Paleo-Ocean, and he based the argument on the topographic asymmetry of the planet, that fundamental 5-kilometre elevation difference between the northern lowlands and the southern highlands, and on the evidence for ancient water erosion already visible in the valley networks mapped by Mariner 9 in 1972. The idea was straightforward. A planet with that much topographic depression, that much evidence of flowing water, and those kinds of drainage networks pointing toward the northern lowlands, had at some earlier time a sea in its northern hemisphere. The response from the planetary science community was skeptical but engaged. And in 1989 and 1993, Timothy Parker at the Jet Propulsion Laboratory published 2 papers that elevated the hypothesis significantly, identifying what he described as 2 distinct ancient shorelines: the older Arabia shoreline, potentially dating to 4 billion years ago, and the younger Deuteronomus shoreline, approximately 3.6 billion years old, based on what he interpreted as geomorphological transitions visible in orbital imagery. Changes in surface texture, albedo and morphology that, he argued, marked the boundary between ancient seafloor and ancient dry land. Parker was careful. He presented his shorelines as tentative identifications requiring further investigation. But the underlying identification was real. The transitions he was seeing were real transitions in the surface record. The question was what had made them. And then the skeptics made a devastating observation. The elevation of Parker's proposed shorelines was not consistent. Tracing the proposed ancient coastline around the entire northern hemisphere, the elevation varied by as much as several kilometres, in some places rising dramatically, in others dipping below the proposed sea level by comparable amounts. On Earth, ancient shorelines are approximately isostatically level. They follow gravitational equipotential surfaces. The same reason that the surface of a standing body of water is flat. Old beach terraces around vanished lakes and seas on Earth can show some variation due to tectonic deformation and isostatic rebound after glacial retreat, but they don't vary by several kilometres across thousands of kilometres of traverse. That kind of variation, the skeptics argued, was more consistent with a random topographic contour drawn across a complicated landscape than with a genuine ancient coastline. The skeptics included Michael Malin and Kenneth Edgett, 2 of the most respected planetary geologists of the era, who used the dramatically higher resolution imagery from the Mars Global Surveyor in the early 2000s to search for the wave-cut platforms, beach ridges, and coastal erosion features that should be present at a genuine ancient shoreline. They found nothing unambiguous. The transitions Parker had identified at lower resolution, Malin and Edgett argued, did not resolve into coastal features at higher resolution. They resolved into general geological complexity without clear marine signatures. The community's momentum shifted decisively towards skepticism through the early 2000s. Papers proposing the ocean continued to be published, but they were working against an institutional headwind. The Mars ocean hypothesis became the kind of idea that serious researchers treated with polite distance. Interesting, possibly not entirely wrong, but certainly not established science. Parker kept what he revised and defended, and pointed to supporting evidence as it accumulated. He had spent years on an argument that the majority of his field thought was probably wrong, and the experience of being on that side of a scientific debate is not comfortable. It requires a specific kind of intellectual endurance. The ability to remain confident in your evidence while acknowledging the legitimate force of the opposition's arguments, and to keep producing new data rather than simply reasserting the old position. What finally broke the stalemate was not more imaging data. It was geophysics. In 2007, Taylor Perrin and Michael Manger, the UC Berkeley geophysicist who will become the central figure in this story's modern arc, published a paper that changed the entire framing of the debate. They asked a question that should have been asked at the very beginning. Before concluding that the proposed shorelines are at inconsistent elevations, have we corrected for everything that could have moved them since they formed? The answer was no. And the thing that hadn't been corrected for was Tharsis. Tharsis is the largest volcanic province in the solar system, a roughly circular region of volcanic uplift approximately 5,000 kilometers across, hosting 3 massive shield volcanoes and, just to the northwest, Olympus Mons. The total mass of Tharsis is approximately 3 times 10 to the power of 26 grams. That is not a geological feature, that is a planetary modification. A mass redistribution of that scale, built up over hundreds of millions of years of eruption, causes a planet's rotational axis to shift, a phenomenon called true polar wander, in which the distribution of mass across a planet changes enough that the planet physically reorients itself relative to its rotation axis. When a planet undergoes true polar wander, features that were originally level relative to the old rotation axis become tilted relative to the new one. A shoreline that was perfectly level when it formed could appear, to an observer who doesn't know about the polar wander, to vary dramatically in elevation across its extent, exactly as Parker's proposed shorelines appeared to do. Perrin and Manga built a geophysical model of the expected polar wander correction for the Tharsis loading event and applied it to the proposed Martian shorelines. When they did, the elevation scatter collapsed. The kilometers of apparent variation in shoreline height, which had been the central piece of evidence against the ocean hypothesis, resolved into a coherent, approximately level ancient coastline. The shoreline was always there. It was always level. Tharsis had tilted it, and nobody had thought to untilt it. This was not a trivial result. Physical models are not obliged to fit real data. When they do, when a model built from independent physical principles produces results that precisely account for an anomaly in a dataset, it means the model is capturing something real about the world. The polar wander correction wasn't reverse engineering the data to make the shoreline work. It was applying a physically motivated correction and watching the shoreline appear where the ocean hypothesis predicted it would be. But even this wasn't enough, because geometry is one thing and physical evidence is another. A geometrically consistent shoreline is a necessary condition for an ancient ocean. It is not a sufficient one. You can draw a geometrically consistent line across a planetary surface without that line representing a coastline. What the Mars ocean hypothesis needed, ultimately, was not a consistent elevation. It needed evidence of coastal processes preserved in the rock itself. It needed something that couldn't be argued away by alternative interpretations of orbital imagery. It needed something direct, something that had been deposited by water in a coastal setting, and that had been lying undisturbed in the Martian subsurface ever since. It needed a beach, and it would take until 2025 for the technology, the mission, and the right landing site to converge in a way that could find one. On the 15th of May, 2021, China's first Mars rover, named Zhurong after the Chinese god of fire, touched down on the southern edge of Utopia Planitia, the largest impact basin on Mars, positioned in the northern hemisphere at coordinates 109.925 degrees east, 25.66 degrees north. The landing site had been chosen with scientific precision. Utopia Planitia sits squarely inside the proposed ancient ocean basin. The Zhurong touchdown point was approximately 280 kilometers north of one of the most debated proposed ancient shorelines, and approximately 500 meters lower in elevation than that shoreline. The rover had been placed, essentially, on what should have been the ancient seafloor, and was pointed in the direction of the ancient coast. Zhurong carried a rover-penetrating radar system, ROPAR, a dual-channel ground-penetrating radar capable of probing up to 80 meters below the surface at high resolution and up to several hundred meters at lower resolution. Ground-penetrating radar works by firing electromagnetic pulses into the ground and listening for reflections from subsurface boundaries, places where the properties of the material change suddenly, such as a transition from one rock type to another, or the boundary between buried sedimentary layers. The time delay between the transmitted pulse and the reflected echo tells you how deep the boundary is. The character of the reflection tells you something about the material. over the course of its single operational year. Zhurong entered a hibernation state in May 2022, from which it never fully recovered. Having travelled 921 metres in total, the rover drove roughly perpendicular to the proposed ancient shoreline, covering its route at a methodical pace and firing radar pulses downward along every metre of the traverse. The traversal geometry was almost ideal for detecting coastal deposits, because driving perpendicular to an ancient shoreline means crossing through the full stratigraphic sequence of nearshore to offshore sedimentary environments, which should be visible in the subsurface as a systematic change in the character of the sedimentary layers. What the radar data showed was a package of thick, layered deposits, visible as dipping reflectors in the cross-section data, angled consistently upward toward the proposed ancient shoreline at approximately 15 degrees. That angle, that specific repeated, sustained 15-degree inclination, maintained across kilometres of radar, traverse in a consistent direction. Let me explain why that number matters. On Earth, coastal beach sediments are deposited in a characteristic geometry. As waves advance and retreat across a shoreline, they transport and deposit sand in wedge-shaped packages that thin away from the beach face and steepen toward it. The angle of these coastal foreset deposits, the term for the inclined layers within a sedimentary package that record the forward migration of a beach face, is diagnostic. It ranges from approximately 10 to 20 degrees on most natural beaches, depending on wave energy, sediment size, and coastal slope. 15 degrees is squarely within the normal range for coastal beach foresets, but angle alone isn't enough. The question is whether the spatial organisation of the deposits is consistent with coastal sedimentation, whether they thicken and thin in the right directions, whether the geometry of the packages makes sense in the context of a prograding shoreline building seaward over time, whether the overall structure is consistent with the full coastal depositional model, rather than just superficially similar in one metric. The international research team, led by Chinese scientists but including Michael Manger of UC Berkeley as a key co-author, compared the Zhurong radar profile systematically against ground-penetrating radar data from a range of terrestrial sedimentary environments. Coastal beaches, river deltas, aeolian dune fields, alluvial fans, lacustrine margins. They were specifically looking for which terrestrial environment produced radar profiles most similar to what Zhurong had recorded in Utopia Planitia. The match to coastal beach deposits was unambiguous. The angular geometry was right. The thickness of the depositional packages was right. The spatial organisation relative to the proposed ancient sea level was right. The way the reflectors organised themselves, thickening in the offshore direction, thinning toward the shoreline, with the characteristic wedge-shaped architecture of a prograding beach face, was all consistent with one and only one interpretive framework. These deposits formed in a coastal zone, adjacent to a large standing body of water. Manger's characterization of the finding as a proper vacation-style beach. Wind, waves, no shortage of sand was not whimsy. It was a technical statement about the completeness of the match. Not a narrow coastal feature, not a margin of uncertainty. A beach in the full sense of the word, with the full suite of depositional signatures that beaches leave in the geological record. Above those beach deposits sits approximately 10 metres of material with no coastal origin whatsoever. Dust storm deposits. Material ejected by meteorite impacts across the northern plains and redistributed by wind. Possible volcanic tephra layers. The accumulated debris of 3 billion years of Martian geological processes laid on top of the ancient beach like a burial shroud, sealing and preserving the coastal stratigraphy beneath. The paper was published in the Proceedings of the National Academy of Sciences in February of 2025. It represented, in my assessment, the definitive moment when the Mars-ocean hypothesis moved from a well-supported scientific argument to established geological fact. You cannot argue with a beach. The deposit is there. It is at the right elevation. It has the right geometry. It is composed of the right materials in the right spatial arrangement. The ocean was real, But here is where the timing delivers its most startling implication, and it is an implication that the popular coverage of this discovery did not adequately emphasize. The beach deposits Zhurong detected do not date to the Noachian period, that earliest and wettest chapter of Martian geological history, spanning from 4.1 to 3.7 billion years ago, when everyone already agreed that Mars had surface water. The sedimentary evidence, based on stratigraphic position relative to known age constraints in the Utopia Planitia sequence, dates the deposits to the late Hesperian, the geological period from approximately 3.7 to 3 billion years ago. The significance of that dating cannot be overstated. The Hesperian period was supposed to be Mars's transition into permanent cold and dryness. The standard model had the Noachian Ocean retreating into permafrost and subsurface ice during the early Hesperian, with only catastrophic, short-lived flood events interrupting a fundamentally frozen surface thereafter. The Hesperian was supposed to be the beginning of the end for Martian surface water, and yet Zhurong found a beach from the late Hesperian, a beach that was actively receiving wave-deposited sediment at a time when Mars was supposed to be well into its desiccation phase, a beach that was part of a coherent ocean, not a temporary flood deposit. A beach, in other words, that tells us the Northern Ocean survived substantially longer than the standard model predicted. The habitability implications of that extended duration are enormous, and they bring us to a question that the science of 2025 and 2026 is now actively trying to answer. Because if the ocean lasted longer than expected, and if Mars was potentially habitable longer than expected, then the window during which life could have arisen, or survived, on Mars was wider than our previous models allowed. How much wider? That depends on understanding something fundamental about the scale of what we're talking about. And scale in this story is everything. Let's stop and be precise about size, because the phrase ancient Martian ocean consistently undersells what the data actually describes. This was not a large lake. This was not a shallow inland sea analogous to the Mediterranean. The body of water that occupied the northern hemisphere of early Mars was, by the most conservative estimates consistent with the available evidence, one of the largest bodies of liquid water that has ever existed in the inner solar system. The most rigorous measurement of the volume of Mars's ancient ocean comes from a 2015 study using a method that is, once you understand it, one of the most elegant pieces of detective work in planetary science. The method exploits the chemistry of water itself, specifically the ratio between two isotopically distinct forms of water that are present in trace amounts in any planetary atmosphere that has experienced prolonged water cycling. Regular water is H2O, two hydrogen atoms bonded to one oxygen atom with a molecular mass of 18 atomic mass units. Semi-heavy water is HDO, one hydrogen atom, one deuterium atom, and one oxygen atom with a molecular mass of 19 atomic mass units. Deuterium is the heavier isotope of hydrogen, with a proton and a neutron in its nucleus rather than just a proton. Because HDO is heavier than H2O, it has a lower vapor pressure, it evaporates less readily, and crucially, it is harder to strip from a planet's atmosphere by solar wind. When the solar wind strips water vapor from an atmosphere, it preferentially removes the lighter H2O molecules and leaves behind a progressively higher ratio of HDO to H2O in whatever water remains. An international team of researchers, using the European Southern Observatory's Very Large Telescope in Chile, along with instruments at the W.M. Keck Observatory in Hawaii and NASA's Infrared Telescope facility in Hawaii, spent 6 years monitoring the Martian atmosphere and mapping the HDO to H2O ratio across different latitudes and seasons. The ratio in Mars's atmosphere today shows a deuterium enrichment approximately 8 times higher than in Earth's ocean water. Running that enrichment backward through the known physics of atmospheric escape gives you a direct measurement of how much water Mars has lost from its atmosphere since the planet formed. The answer is staggering. Mars has lost the equivalent of a global layer of water approximately 140 meters deep, meaning if you spread that lost water uniformly across the entire surface of Mars, it would form a layer 140 meters thick. That is the water that escaped to space. The water that actually existed on the surface in the form of an ocean was concentrated in the northern lowlands rather than spread uniformly, which means the ocean depths were far greater than that average figure implies. Working out the ocean geometry, given what we know about the topography of the northern lowlands and the proposed ancient shorelines, gives a volume of at least 20 million cubic kilometers. In some regions, the ancient ocean reached depths exceeding 1.6 kilometers. And if you accept the higher estimates from studies that incorporate additional water inventory constraints, the maximum plausible volume is closer to 124 million cubic kilometers. Let's compare those numbers to something familiar. The Atlantic Ocean on Earth contains approximately 310 million cubic kilometers of water. The Arctic Ocean, which is geographically smaller and shallower, contains approximately 17 million cubic kilometers. So Mars's ancient ocean, at the conservative estimate of 20 million cubic kilometers, was roughly comparable in volume to Earth's Arctic Ocean, and at the upper estimate of 124 million cubic kilometers, it held nearly 40% of the Atlantic's volume. But here is the comparison that actually matters, the one that captures the true scale of what early Mars looked like from orbit. The Atlantic Ocean covers approximately 20% of Earth's total surface area. Mars's ancient northern ocean, depending on which shoreline estimate you accept, covered between 19 and 36% of Mars's total surface area. The geographical footprint was Atlantic scale on a planet with less than 3 times the surface area of Earth's continents combined. A 2010 study by Giovanna D'Achille and Brian Hynek at the University of Colorado adds a beautiful independent corroboration to these volume estimates. They use Geographic Information System technology to map and characterize 52 ancient river delta systems on Mars. The distinctive fan-shaped deposits where rivers decelerate upon entering standing water and drop their sediment loads. These delta systems were distributed across the entire Martian surface, formed at different times, in different geological contexts, fed by different drainage basins. They had nothing in common except where they terminated. 17 of those 52 delta systems converged on a common elevation band that matched the proposed Deuteronomus shoreline. Parker's younger shoreline dated to approximately 3.6 billion years ago. The average termination elevation of the deltas was consistent to within a few hundred meters across the entire planetary distribution. 17 independent river systems drawing water from catchments thousands of kilometers apart, all depositing their sediment at the same elevation at the same time. The statistical probability of that convergence occurring by coincidence, without a common base level to drive it, is not seriously entertained by any geologist who has worked through the numbers. Those rivers were all flowing into the same body of water. That body of water had a surface. That surface was, as all large standing bodies of water have, a gravitational equipotential, what we would call a sea level. Mars had a sea level. Think about what that really means. Sea level is not just a measurement, it is an architectural principle for a living world. It is the thing that organises coastal gradients, determines where nutrients concentrate in the water column, controls where sunlight can reach the seafloor and drive photosynthesis in shallow water, sets the conditions for the richest and most chemically diverse interface environments. Earth's continental shelf regions, the shallow water zones where the seafloor is less than 200 meters below the surface, support an estimated 40% of all marine biodiversity despite covering only 8% of the ocean's total area. They do this because shallow coastal water is where everything happens biologically, where rivers bring nutrients, where light penetrates to the bottom, where tidal and wave energy drives constant mixing and refreshment of the water column. Mars had an ocean large enough and shallow enough in its marginal regions to have extensive coastal shelf environments that, in terms of their physical and chemical structure, were not categorically different from the shallow marine environments on Earth. where, 3.5 billion years ago, life was already thriving. The 2026 topographic shelf analysis makes this architectural similarity even more explicit. Researchers examining the fine-scale topography of the northern lowlands identified a distinct zone of low slope and gentle gradient between approximately -1,800 and -3,800 meters elevation. A broad, flat region that matches the characteristic profile of a continental shelf. On Earth, the continental shelf is the submerged margin of a continent, built up over millions of years by sediment deposition in relatively shallow water. It is the most geologically recognizable signature of a long-lived, stable ocean. Mars has this structure. The Martian continental shelf, if we can call it that, suggests an ocean that was stable for long enough, millions to tens of millions of years at minimum, to build an extensive shallow water platform around its margins. This is not a fleeting flood. This is not a temporary catastrophic release of subsurface water that lasted a few years before refreezing. This is a persistent, architecturally complex ocean, with a shelf, with a coastline, with beaches, with river deltas, with a sea level. An ocean that, by the evidence of Zhurong's beach deposits, survived into the late Hesperian, meaning it persisted for somewhere in the range of 500 million to 1 billion years. And then, over the course of geological time that is both long by human standards and brutally short by planetary standards, it died. The mechanism of its death is one of the most important stories in planetary science, because it involves the precise sequence of geological events that separates a living world from a dead one. And it begins not with something that was lost from Mars, but with something Mars never managed to keep. There is a machine running inside the Earth right now that most people never think about. It has been running, more or less continuously, for approximately 3.5 billion years. It will continue running for at least another billion years. You cannot feel it. You cannot hear it. But every piece of life on this planet, including you, exists partly because it has not stopped. The machine is the geodynamo, the self-sustaining magnetohydrodynamic engine at the heart of the Earth, a vast system of convecting liquid iron and nickel in the outer core, churning and cycling under the influence of both thermal convection and the Coriolis force of Earth's rotation, generating by its motion an electromagnetic field that extends approximately 60 kilometers into space and deflects the continuous stream of charged particles emitted by the Sun. The solar wind, at Earth's orbital distance, carries ions with enough energy to strip lighter molecules, primarily hydrogen, from a planet's upper atmosphere if those molecules are directly exposed to the particle flux without magnetic deflection. The geodynamo prevents this. The magnetic field catches the solar wind and deflects it around the planet, channeling the most energetic particles into the Van Allen belts and allowing the bulk of the atmosphere to remain intact. Earth's magnetic field at the surface averages between 25 and 65 microteslas. The geodynamo generating it is powered by the heat released by radioactive decay of uranium, thorium, and potassium in Earth's interior, a heat source with a half-life measured in billions of years, which is why the engine has run continuously for billions of years, and will continue to do so. The convection in the outer core, driven by that heat, is the perpetual motion that drives the field. Mars had this engine too. We know this because the evidence is written in the oldest rocks on the planet, the magnetized minerals in the southern highland terrain, some of the most ancient crust on Mars, dating to 4.1 billion years or more, are oriented in patterns consistent with magnetization by a strong, coherent global magnetic field. In some regions, the remnant field preserved in those ancient rocks was apparently twice the strength of Earth's current surface field. Early Mars was a genuinely well-protected planet with a magnetosphere that deflected the solar wind and kept its atmosphere intact. And then the machine stopped. The reason involves the composition and thermal history of Mars's core, and specifically a piece of metallurgical chemistry that was worked out in a landmark 2022 study led by Shunpei Yoku of the University of Tokyo. Yoku's team didn't go to Mars. They built Mars's core in a laboratory in Tokyo, creating a mixture of iron, sulfur, and hydrogen, the three components believed to be present in the early Martian core, and subjecting that mixture to the pressures and temperatures expected deep inside a planet of Mars's mass. What they found was a core material that, when heated to the temperatures of a young planet's interior, produced convective flows, exactly the kind of flows that power a planetary dynamo. The difference in density between hydrogen-rich iron and sulfur-rich iron caused the lighter fraction to rise and the heavier fraction to sink, creating the same basic convective architecture that drives Earth's geodynamo. The Martian core, in its early hot state, was a working dynamo. It was generating a magnetic field. Mars was protected, but then the separation completed. The hydrogen-rich and sulfur-rich components of the molten iron finished unmixing, segregating into distinct layers like oil separating from vinegar, and the density gradient that had been driving the convection disappeared. Without a density gradient, there is no buoyancy-driven flow. Without flow, there is no dynamo. Without a dynamo, there is no magnetic field. The critical difference between Mars and Earth is why this happened on Mars and didn't happen on Earth. Earth's outer core convection is driven primarily by the release of latent heat from the solidification of the inner core and by radioactive decay, heat sources that are self-replenishing on geological timescales. Mars has a similar inventory of radioactive elements, but its smaller size, just 11% of Earth's mass, means it has a larger surface area to volume ratio, and therefore loses its internal heat to space much faster. The Martian core cooled faster. The initial chemical convection drove the iron-sulfur separation to completion more rapidly, and once the separation was complete, there was no secondary heat source strong enough to sustain convection. The death of the Martian dynamo was not a sudden catastrophic event. It was a gradual decline over perhaps 200 to 300 million years, spanning the late Noachian and early Hesperian periods, roughly 4.1 to 3.7 billion years ago, during which the magnetic field became progressively weaker, patchier, and less effective at deflecting the solar wind. As the field weakened, more and more of the upper atmosphere was directly exposed to the solar particle flux. The hydrogen at the top of the atmosphere, primarily present as water vapour, was stripped away. The oxygen, stripped of its hydrogen partner, either escaped independently or reacted with the surface iron to form the iron oxide that makes Mars red. The surface is rust-coloured because it got its oxygen from water. The rust is the chemical residue of an ocean. Stripping the atmosphere took time. Mars's atmosphere didn't disappear overnight. Measurements of argon isotopes in the Martian atmosphere, specifically the ratio of the heavier argon-38 to the lighter argon-36, where the solar wind preferentially removes the lighter isotope, tell us that Mars has lost approximately 65% of its original argon inventory. That's a substantial but not total loss, and the rate of loss depends on the solar wind flux and the degree of magnetic protection at any given time. The atmosphere that existed in the Hesperian, when Zhurong's beach was being deposited, was thinner than the Noachian atmosphere, but not yet as thin as today. It was enough, apparently, to maintain liquid water in the northern basin under the right conditions. But what were those conditions? How was a northern ocean still present 3 billion years ago, when the magnetic field had been absent for over 700 million years, and the atmosphere was actively being eroded? The answer requires understanding the other major geological force operating on early Mars, the entity that was simultaneously building the most dramatic landscape feature in the solar system, and, as a side effect, keeping a dying ocean alive. That entity is Tharsis, and its role in the Mars ocean story is both more complex and more consequential than most accounts of Martian water history have captured. Tharsis is, by any reasonable measure, the most extreme geological feature in the solar system. Not the tallest mountain, that distinction goes to Olympus Mons, which is part of the Tharsis complex but is technically a separate shield volcano. Not the deepest basin, that's Hellas Planitia in the southern hemisphere. Tharsis is extreme in a different way. It is extreme in its totality, in the sheer accumulated scale of its volcanic output, in the completeness with which a single geological province has modified an entire planetary body. The Tharsis Plateau is roughly circular, approximately 5,000 kilometers in diameter, and stands up to 7 kilometers above the mean Martian surface elevation. Within it sit 4 massive shield volcanoes, Olympus Mons at 21, 9 kilometers height and approximately 600 kilometers base diameter, and the 3 Tharsis Montes, Ascraeus, Pavonis and Arsia, rising between 14 and 18 kilometers above the datum. The total mass of the Tharsis complex is approximately 3 times 10 to the 26th grams. To put that in terms of something comprehensible, it would take approximately 10,000 copies of Earth's entire Himalayan range to equal the mass of Tharsis. It is a feature so massive that it has deflected the entire crustal structure of the planet, tilting the northern lowlands and triggering the polar wander that distorted the ancient shorelines. Building Tharsis required erupting that mass of volcanic material into the surface. Eruptions at that scale do not just produce rock. They produce gases in enormous quantities: carbon dioxide, water vapour, sulfur dioxide, hydrogen sulfide, and a range of other volatiles that, once in the atmosphere, participate in the complex photochemical and radiative processes that determine a planet's climate. Tharsis, over the hundreds of millions of years of its most active construction phase during the Noachian and early Hesperian, was a planetary-scale greenhouse gas factory. In 2018, Michael Manga and colleagues published a paper in Nature. One of the most important papers in the Mars ocean literature of the past decade, proposing a new timeline for the relationship between Tharsis volcanism and the ancient Martian oceans. The traditional model had assumed Tharsis formed rapidly and early, before the oceans, and that the oceans formed in the topographic depression created by Tharsis's gravitational loading of the crust. Manga's model proposed the opposite. The ocean formed before and simultaneously with Tharsis, not after it. This reversal of the conventional timeline, which might initially appear to be a minor technical revision, has profound implications for how long Mars's ocean could have been sustained. If the oceans formed simultaneously with Tharsis, then the entire greenhouse gas output of the Tharsis volcanic system, the CO2, the SO2, as water vapour released by eruptions, was being injected into the atmosphere during the same period when the ocean existed. Tharsis was, in effect, providing a continuous climate subsidy to the ocean. Every major eruption phase added greenhouse gases that thickened the atmosphere, increased the surface temperature, and extended the window of time during which liquid water could exist at the surface. This matters enormously for one of the central puzzles in early planetary climate science, the faint young sun problem. The Sun 4 billion years ago was putting out approximately 70% of its current luminosity. Mars, at its greater distance from the Sun, was receiving less solar energy than Earth receives today, even from the current, brighter Sun. Simple radiative balance calculations suggest that early Mars should have been permanently frozen, that the solar energy available was insufficient to maintain surface temperatures above the freezing point of water, and yet the geological record is unambiguous. Mars had liquid water extensively and for a long time. Something was keeping early Mars warm enough for liquid water despite the weak young sun. On Earth, the same problem exists and is partially solved by geological evidence for a thicker early CO2 atmosphere. On Mars, Tharsis may have been doing something analogous, providing a continuous outgassing supply of greenhouse gases that maintained a thick enough CO2 atmosphere to trap sufficient heat for liquid water. The system was not a stable equilibrium. It was a dynamic balance between volcanic outgassing, adding greenhouse gases, and atmospheric escape removing them. But Tharsis was, for hundreds of millions of years, strong enough to tip that balance in favour of habitability. The evidence for this is embedded in the very geometry of the Martian valleys and channels. The valley networks that drain into the Northern Ocean are not uniformly distributed in time. They cluster during the Noachian and early Hesperian, precisely the periods of most intense Tharsis volcanism. As Tharsis eruption rates declined in the mid to late Hesperian, the frequency of valley network formation declined as well, as though the climate was directly responding to the volcanic thermal subsidy. The Hesperian outflow channels, those enormous flood features carved by catastrophic releases of subsurface water, represent a different regime, not the gentle sustained fluvial activity of a warm, wet climate, but episodic, violent, short-lived floods driven by volcanic heating of subsurface ice reservoirs. These are the geological signature of a planet already cold but not yet entirely frozen, experiencing convulsive episodes of temporary surface water release between increasingly long dry intervals. Zhurong's beach fits into this picture as the last chapter of the ocean's sustained existence. By the late Hesperian, the ocean was smaller than it had been at its Noachian maximum. The shoreline had retreated from its greatest extent. The climate was marginal, cold enough that the ocean probably had seasonal or permanent ice cover in many regions, warm enough in others to maintain open water. The beach deposits Zhurong found represent a shoreline that was actively receiving wave energy, which requires open, ice-free water at a time when the planet was in the closing stages of its habitability, and then Tharsis's eruption rate dropped below the threshold where it could sustain the greenhouse balance. The atmosphere thinned past the critical point. The ocean froze, and then it sublimated, and then the water vapour was stripped by the solar wind, and then there was nothing. The rust-coloured surface you see in photographs today is in part the chemical aftermath of that final desiccation. Iron oxidised by the oxygen liberated from water vapour as hydrogen escaped to space. Mars didn't lose its ocean because the water evaporated in the sun. It lost it because the geological machinery that was keeping it liquid ran down. And once the water was gone from the surface, the combination of low atmospheric pressure and continuous solar wind stripping ensured it could never return. That is a story about size, about how a planet that was just slightly too small to retain its internal heat for long enough found itself, 3 billion years ago, crossing a threshold from which there was no return. The ocean wasn't taken, it was abandoned, slowly, by a planet that simply ran out of the geological energy required to keep it. There is a category of scientific argument that is qualitatively different from others, and the Mars-ocean debate belongs firmly in it. This is a debate that has consumed significant portions of careers, debate in which being right required being dismissed for a decade first, and in which the evidence that would ultimately vindicate the hypothesis arrived from directions that the people who'd spent their careers building it had no control over, carried by a Chinese rover that nobody in the American planetary science community had any role in designing or operating. Timothy Parker is a planetary geologist at the Jet Propulsion Laboratory in Pasadena who spent the better part of his career arguing for the existence of ancient Martian shorelines. His 1989 and 1993 papers identifying the Arabia and Deuteronomus shorelines were among the foundational documents of the modern Mars-ocean hypothesis. The argument was careful and the evidence was real. The geomorphological transitions he identified in the orbital imagery were genuine transitions in the surface record, but the inability to explain the elevation inconsistency meant that the argument was never definitively settled, and in the absence of definitive settlement, the field's default position gradually shifted towards skepticism. Parker published follow-up work through the 1990s and 2000s. He revised his shoreline interpretations as better imagery became available. He argued, patiently and in detail, that the elevation inconsistencies had geological explanations. He worked in the productive and uncomfortable space of a scientist who is probably right, but cannot yet prove it conclusively, and who has to continue working under the assumption that the evidence will eventually accumulate, while also accepting that the majority opinion in his field currently disagrees with him. The experience of that position is worth naming clearly. Science is often described as a purely rational enterprise, where evidence is evaluated dispassionately and the best argument wins. It is also, simultaneously, a deeply human social enterprise where institutional momentum matters, where the default of a field's senior researchers shapes what junior researchers are willing to put in print, and where being persistently associated with a controversial hypothesis can narrow career opportunities in ways that have nothing to do with the quality of the underlying work. Parker continued publishing, but the weight of the field's skepticism was a constant professional headwind. Brian Hynek and Gaetano Diaquile's 2010 delta mapping study, with its 52 river delta systems converging on a common ancient sea level, came from a different direction than Parker's work and provided independent statistical corroboration that was harder to dismiss than the original shoreline identification. Hynek had approached the question geomorphologically rather than through shoreline tracing, and the convergence of his delta termination elevations with Parker's proposed deuteronolous shoreline was exactly the kind of independent cross-check that gives a hypothesis structural support. But it was Michael Manger who, in my reading of the past 20 years of Mars ocean science, made the sequence of contributions that most decisively moved the hypothesis from contested to essentially settled. Manger is a geophysicist at the University of California, Berkeley, with a scientific career that has spanned earthquake triggering, volcanodynamics, and planetary geophysics. His 2007 polar wander correction paper, published with Taylor Perron, was the first major contribution, resolving the elevation inconsistency that had been the central technical objection to the shoreline identification. His 2018 Tharsis Ocean timing paper in Nature reorganized the entire temporal framework for understanding how Mars's oceans and volcanic history interacted, and his role as a co-author and co-interpreter on the Zhurong beach deposit paper in 2025 brought him directly into the moment of evidential confirmation. There is something I find genuinely moving about the arc of Manger's involvement in this question. He has spent approximately 2 decades working on a problem that required, at every stage, convincing a field that was constitutionally skeptical of the answer. He built physical models that corrected for phenomena the original analysis hadn't accounted for. He proposed new timelines and new causal relationships that required revising deeply embedded assumptions about Martian geological history. He published consistently and clearly, and without the kind of overclaiming that would have made his work easy to dismiss. And then a rover from a country that wasn't involved in any of his previous work landed on the ancient seafloor he had spent 2 decades arguing for, drove toward the shoreline his models had predicted, and found a beach. I think about what it feels like to receive that call. To be the person who, when a Chinese graduate student reaches out because they need someone who understands the geophysics of ancient Martian ocean margins to interpret their rover data, discovers that the radar profile they're looking at is a perfect match for the coastal deposits he's been predicting for 20 years. The satisfaction would be real. It would also be, I suspect, complicated by the 20 years of working against the grain, and by the knowledge that the confirmation came from a mission he had no involvement in building, landed on a planet he will never visit, to interpret data from an ocean that has been gone for 3 billion years. Science does not always vindicate you cleanly or quickly. It does not always deliver confirmation through the channels you expected. Sometimes the beach finds you from the other side of the world, in a radar profile sent back by a rover that went to sleep 15 months after it landed and never fully woke up again. But the beach is there, and the fact that it is there, that the evidence was preserved, that the mission was designed to detect it, that the physical models were ready to interpret it, is the cumulative result of 50 years of work by dozens of scientists who argued, sometimes against the consensus, that Mars had an ocean. Parker was right, Hynek was right, Manger was right, and the fact that being right required that much sustained effort against that much institutional resistance across that much time says something important about how science actually works and about the peculiar kind of stubbornness that good scientists require. The ocean did not disappear cleanly from Mars. It didn't evaporate one day and leave a dry planet the next. The geological record suggests a retreat that was both gradual and punctuated, a slow general drying interrupted by episodes of dramatic but temporary rehydration as subsurface water reservoirs were violently released by volcanic heating or meteorite impacts, and when the surface ocean finally gave way entirely to frozen permafrost, the water didn't all escape to space. A substantial fraction of it went down into the crust, where it has been ever since, frozen in the deep regolith or in geothermally active regions, potentially still liquid today. The volume of water currently visible in Mars's polar ice caps has been measured by orbital radar sounding. The SHARAD and MARSIS instruments on board NASA's Mars Reconnaissance Orbiter and ESA's Mars Express at approximately 2.85 million cubic kilometres. That is a number comparable to the volume of the Antarctic ice sheet on Earth. But those polar deposits represent only the water that is visible at the surface. The Martian cryosphere, the layer of permanently frozen ground extending from the surface to depths of several kilometres, potentially covering most of the planet at latitudes above 30 degrees, may contain substantially more. The MARSIS instrument, in its most celebrated single result, detected what appeared to be a persistent radar reflection anomaly approximately 1.5 kilometres beneath the South Polar layered deposits, covering a roughly elliptical area about 20 kilometres across. The reflection had the radar signature characteristic of liquid water, a high reflectivity return consistent with a material with a high dielectric constant which liquid water possesses and ice and rock do not. The feature was interpreted, in a 2018 paper in Science, as a subglacial lake, liquid water kept above the freezing point by the pressure of the overlying ice and possibly by geothermal heat from below. The discovery was controversial, and it remains so. Subsequent papers published between 2021 and 2023 proposed alternative explanations. Specific clay mineral assemblages or carbon dioxide ice deposits with unusual electromagnetic properties that could produce similar radar signatures. The debate has not been fully resolved, but additional analysis of the MARSIS dataset produced a cluster of similar reflection anomalies distributed around the South Polar region, suggesting multiple potentially liquid zones rather than a single isolated feature. Whether these are genuinely liquid water or some unusual solid material with water-like radar properties is a question that requires direct sampling to answer definitively. What the subsurface water evidence adds to the ocean narrative is conceptually important, regardless of whether the specific MARSIS anomaly is liquid water or not. When the surface ocean retreated, the water budget of Mars did not simply balance out as atmospheric escape. The isotopic water loss measurements tell us Mars has lost a specific amount of water to space. The polar ice caps tell us how much is currently frozen at the surface. The gap between those two numbers represents water that has gone into the crust, water that is frozen in the deep permafrost, or potentially liquid in geothermally heated subsurface zones, or chemically bound into hydrated minerals throughout the upper crust. That subsurface water is not biologically irrelevant. On Earth, the deep biosphere, microbial communities living in fractured rock at depths of up to 5 kilometres, has been one of the most significant discoveries in astrobiology of the past 30 years. These communities live without sunlight, drawing energy from the chemical gradients between reduced minerals and oxidized water, metabolizing at rates so slow that their generation times are measured in thousands of years, but maintaining genuine metabolic activity and biological viability. They represent, in aggregate, a biomass comparable in some estimates to all surface life on Earth. If life ever arose in the warm, chemically complex coastal environments of early Mars, if the late Hesperian Ocean was a functioning biological system, even at the most primitive microbial level, then the question of whether any of that life followed the water downward as the surface dried is not absurd. It is a genuine scientific hypothesis with no evidence against it. Life following water into the deep crust, slowing its metabolism as temperatures dropped and chemical energy became scarcer, potentially surviving today in the warmest and most geochemically active subsurface zones. This is not science fiction. It is a direct extrapolation of what we know about life's behaviour on Earth, applied to the specific geological trajectory of Mars. Whether it happened is another question entirely, and the answer to that question may be closer to resolution than most people realise. In September of 2025, NASA announced what acting NASA Administrator Sean Duffy described as the closest we have ever come to discovering life on Mars. The announcement concerned a rock sample named Sapphire Canyon, collected by the Perseverance rover in July 2024 from a geological formation called Bright Angel in Jezero Crater, an ancient river delta where liquid water last flowed between 3.2 and 3.8 billion years ago. A paper published in Nature on September 10, 2025, described what Perseverance's Sherlock instrument had detected in that sample. The rock was a mudstone, fine-grained sediment deposited in still or slow-moving water, exactly the kind of depositional environment that would trap and preserve organic material and biological byproducts if any were present. Within the mudstone, the Sherlock Raman spectroscopy instrument detected organic carbon compounds with the chemical structure characteristic of biology, though also potentially producible by abiotic chemistry. But it was not the organic carbon alone that elevated this sample to its current scientific status. What the instrument detected alongside the organics was a spatial pattern. Green spots on the reddish mudstone distributed in what the research team described as a leopard spot pattern. Clusters of two specific minerals, vivianite, an iron phosphate, and greigite, an iron sulfide. These minerals are chemically significant in a specific context. On Earth, vivianite and greigite form in alkaline, reducing environments where organic matter and iron minerals are interacting through microbially mediated redox reactions. Chemical reactions that microorganisms use to extract energy from their environment, oxidizing organic compounds and reducing iron minerals in the process. The specific spatial pattern of vivianite greigite in the Bright Angel mudstone, the leopard spots, matches the pattern produced by iron-reducing bacteria on Earth when they metabolize organic compounds in fine-grained sediment. The geometry of the mineral distribution, the association with organic carbon, the specific mineral identities, all are consistent with biological origin. They are also consistent with certain abiotic chemical pathways. The same minerals can form without biology, under the right temperature and pressure conditions, through purely chemical reactions. The research team, with appropriate scientific caution, described the finding as a potential biosignature rather than confirmed evidence of life. Lead author Joel Hurwitz was direct about the ambiguity. The combination of chemical compounds we found in the Bright Angel formation could have been a rich source of energy for microbial metabolisms. Just because we saw all these compelling chemical signatures in the data didn't mean we had a potential biosignature. We needed to analyse what that data could mean. What the Sapphire Canyon sample represents is the strongest evidence yet that Mars, at the time of Jezero Crater's ancient lake, 3.2 to 3.8 billion years ago, roughly contemporaneous with the late Hesperian Northern Ocean, was hosting chemistry that was at minimum consistent with biological activity, and that is more parsimoniously explained by biology than by abiotic processes alone. It is not proof of life. It is the kind of evidence that, in a geological sample returned from Earth, would trigger an intensive investigation by astrobiologists. And the Sapphire Canyon sample is still on Mars, sealed in a tube inside Perseverance, waiting for the sample return mission that will bring it to Earth labs, where the full analytical arsenal of modern astrobiology can be applied to it. That day is coming. It is delayed, it is underfunded, it is frustratingly slow in its progress through the complicated machinery of international space policy and budget negotiations. But the sample is sealed, the evidence is preserved, and when it arrives on Earth, it will be the most intensively studied geological specimen in human history. Let's place this entire story in the one context that makes it most stark, 500 million years. That number, which appears in the title of this documentary, is worth unpacking with precision because its significance operates on multiple levels simultaneously, and understanding all of them changes how you interpret everything we've discussed. 500 million years ago on Earth, the Cambrian explosion was underway. The fossil record, which before this period preserved almost exclusively the traces of single-celled life and simple colonial organisms, suddenly filled with the body plans of complex, multicellular, differentiated animals, trilobites with compound eyes and articulated exoskeletons, anomalocarids with grasping appendages and stereoscopic vision, mollusks, echinoderms, early chordates whose descendants would eventually develop into every vertebrate alive today. The Cambrian explosion was not an accident. It was the result of approximately 3 billion years of evolutionary groundwork. 3 billion years during which single-celled life had been building the biochemical toolkit that complex multicellular organisms would eventually inherit. At the same moment that Mars's ocean was in its final phase, 3 billion years ago when the beach Zhurong found was still receiving waves, Earth's ocean contained nothing more complex than microbial mats, bacteria, archaea, single-celled eukaryotes perhaps just beginning to diversify. The organisms alive on Earth at the time of Mars's last beach were not animals. They were not plants. They were the fundamental unit of life, the self-replicating, membrane-bounded, metabolically active cell. And they had been that for 1 billion years already. This is the frame within which any honest discussion of potential Martian life must operate. When we ask whether life could have existed in the Martian ocean, we are not asking whether there were fish or algae or anything that would be recognizable to a non-scientist as living. We are asking whether the ocean could have supported metabolism, whether it could have supported the chemistry of self-replication, whether the molecular logic of biology, the encoding of information in polymers, the catalysis of chemical reactions by proteins, the extraction of energy from chemical gradients, could have gotten started in the warm, mineral-rich, energy-bathed coastal zones of the Hesperian Northern Ocean. That is a different question from what people often imagine when they hear life on Mars. It is a more humble question in some ways, and a more profound one in others, because the origin of life, that first moment when chemistry became biology, when a self-replicating molecule emerged in a pool of warm water, is still one of the deepest unsolved problems in all of science. We don't know with certainty how life began on Earth. We have plausible pathways, hydrothermal vent chemistry, alkaline ocean floor reactions, UV-driven organic synthesis in shallow tidal pools, but we don't have a confirmed mechanism. If life arose on Mars independently of life on Earth, it would represent not just confirmation that life exists elsewhere in the universe, but confirmation that the origin of life is not a singular miraculous accident, but a reliably reproducible outcome given the right starting conditions. That would be, without exaggeration, the most important discovery in the history of human knowledge. Now, let me be precise about the current state of the evidence, because the biosignature announcement from September 2025, the Sapphire Canyon leopard spots, is genuinely significant, but also genuinely inconclusive, and conflating significant with conclusive does a disservice to both the scientists involved and to the public trying to understand what has actually been found. What has been found, as of mid-2026, is this: a Hesperian-aged mudstone from an ancient lake bottom in Jezero crater contains organic carbon and a specific spatial pattern of iron minerals that, on Earth, is most commonly produced by iron-reducing bacteria. The finding is the strongest evidence yet for possible ancient biological activity on Mars. It does not prove that life existed on Mars. It proves that the chemistry in that specific rock at that specific time was doing something that life is very good at doing, and that abiotic chemistry can do under specific conditions. To distinguish between the biological and abiotic interpretations definitively requires the kind of analytical capabilities: isotopic analysis, molecular structure characterization, spatial distribution mapping at the nanometer scale, that do not fit on a Mars rover and require a terrestrial laboratory. Perseverance also found in March 2025 long-chain organic molecules called alkanes in mudstone samples from Gale Crater, a result published in the Proceedings of the National Academy of Sciences. Alkynes of the chain lengths detected are, on Earth, primarily produced by biological processes. They can also be produced abiotically. Same interpretive challenge, same analytical requirement. The pattern that emerges from the 2025 discoveries is consistent and increasingly difficult to explain without considering biology as a contributing factor. Multiple independent samples from multiple different ancient aquatic environments, dated to the period when the Northern Ocean was still present or recently retreated, showing organic chemistry of the kind that life produces. This is not a single anomalous finding that might be explained by a one-off abiotic process. It is a pattern across sites and sample types that is, to use the careful language of the scientists involved, more consistent with biological processes than with abiotic chemistry, though abiotic explanations cannot be ruled out. The Mars sample return mission, when it arrives, will resolve this. The Sapphire Canyon sample, examined by instruments capable of resolving individual molecules and measuring isotopic fractionation at the level of precision required to distinguish biological from abiotic organic chemistry, will give an answer that the Sherlock instrument on Perseverance simply cannot provide. The isotopic composition of the carbon in those organic molecules is the key measurement. Biological carbon metabolism preferentially incorporates the lighter carbon-12 isotope over the heavier carbon-13, producing a characteristic isotopic depletion pattern, a carbon-13 deficit, that is diagnostic of biological processing. If the organics in Sapphire Canyon show that depletion, it is extremely strong evidence for biology. If they don't, the abiotic explanation becomes much more likely. That measurement requires a mass spectrometer sensitive enough to detect parts per thousand variations in carbon isotope ratios. An instrument that weighs tens of kilograms and requires controlled laboratory conditions. It cannot be sent to Mars in any currently designed rover. The sample must come to the instrument. The Mars sample return mission, as of 2026, has been redesigned following a 2024 independent review that found the original architecture was going to cost approximately $11 billion and take until 2040 to return samples. The revised architecture, which is still being finalised, aims to reduce both the cost and the timeline. The earliest plausible return under current planning is the mid-2030s. That is, measured against the urgency of the scientific question, an uncomfortable amount of time to wait. But it is finite. The samples are sealed, the clock is running, and there is a larger question that this story of Mars's ancient ocean ultimately forces us to ask, not just about Mars, but about the universe we live in, and about the frequency and fragility of conditions like those that produced us. Mars and Earth formed from the same material, at similar distances from the same star, at the same time. They received comparable initial endowments of water, organics, and energy. For roughly the first billion years of the solar system's history, both planets had surfaces that were, in the broad geological sense, wet and potentially habitable. Earth sustained those conditions for 4 billion years. Mars sustained them for approximately 500 million to 1 billion years and has been dry and frozen for the 3 billion years since. The difference between these outcomes traces back, with increasing clarity as the science develops, to a single fundamental variable: mass. Earth is approximately 9 times more massive than Mars. That mass difference means Earth retained its internal heat for long enough to maintain a geodynamo which protected an atmosphere, which kept surface temperatures above the freezing point of water, which kept the oceans liquid, which created the stable, continuous environmental conditions within which life could not only arise but persist and diversify over 4 billion years. Mars was simply too small. The heat leaked away too fast. The core separated too soon. The magnetic field faded. The atmosphere eroded. the ocean retreated, and by 3 billion years ago, whatever life may or may not have existed in the warm coastal waters of the Hesperian Ocean was either gone entirely or retreating with the water into the cold darkness of the deep crust. The lesson that Mars teaches, not as a metaphor but as a direct physical demonstration of planetary evolution, is that habitability is not a binary state. It is not something a planet either has or doesn't have. It is a process, maintained by the ongoing operation of geological machinery. It requires a sustained energy budget for interior heat. It requires a magnetic field to protect an atmosphere from stellar wind erosion. It requires ongoing volcanic recycling of greenhouse gases to keep surface temperatures within the liquid water range. It requires a large enough moon, perhaps, to stabilize the axial tilt and prevent the wild climate oscillations that would otherwise disrupt surface conditions on multi-million-year timescales. Earth has all of these things. Mars had some of them for a while, but not for long enough. And the question of how common, among all the rocky planets orbiting stars throughout the galaxy, is the specific combination of properties that Earth has, large enough, with the right internal composition, with a stabilizing large moon, at the right orbital distance, with the right recycling mechanisms, is the deepest question in the young science of exoplanet habitability. And it is a question that Mars is teaching us how to ask. We are not the first wet world in this solar system. We are the one that lasted. And whether there are others like us in the galaxy, worlds that got the balance right, that maintained their oceans and their atmospheres and their magnetic fields long enough for complexity to arise, depends on understanding precisely why Mars got it wrong. We are, right now in 2026, closer to answering that question than at any previous moment in human history. The beach is found. The biosignature candidates are in their tubes. The analytical tools exist. The missions are being planned. The scientists who spent decades arguing for the ocean have been vindicated. And the scientists now building on their work are asking the questions that follow. What remains is a decision, not a scientific decision. The science knows what to do. A human decision about whether answering the most profound question our species has ever asked is worth the sustained commitment of resources and attention that it requires. I believe it is, and I believe that anyone who genuinely understands what Mars is telling us, that we are not alone in having had an ocean, that there was a time when two worlds in our solar system had beaches and rivers and coastal chemistry and the possibility of life, cannot look at that story and conclude that the answer to what was in that ocean is not worth finding. The northern plains of Mars stretch flat and cold and silent right now, under a sky the colour of a bruise at sunset. 10 metres below the surface, at the edge of a basin that was once a sea, the sediment layers are still there, angled at 15 degrees toward a shoreline that no longer exists, perfectly preserved in the cold and dark, holding whatever chemistry the late Hesperian Ocean left behind. 3 billion years of silence, waiting. And for the first time in the history of our solar system, something with the curiosity and the tools to go and ask the question is alive and building the machines to do exactly that. There is a beach on Mars. There was an ocean. It lasted 500 million years. And we have not yet found out what was swimming in it. That is not an ending. That is the beginning of the most important investigation in the history of science. Go look.